Okay, good afternoon. Welcome to the class once again. Today we are going to discuss about the last portion of the topic that we were covering, which is the system modeling. In this topic, we were focused on very much the UML class diagrams. In the previous lectures, we mentioned about the UML classification. Now we know that UML is constantly evolving. It's not like it's stopped. I think the next version is going to come out really soon. Let's check out actually. I'm not quite sure about the dates. UML. So the one that we are using right now is released on 2015. That is 2.5. But I know that a new one is under construction. They're gonna release it very soon. So I'm not quite sure about the date. So the last version, it's 2.5, which is the one that we are using, is released in 2015. A new version is on the way, but I'm not finding the way. I read in some articles that they are doing a new version of it, and maybe new diagrams will be added. We'll see what happens when this version comes. But right now we have 5 main diagrams that dominate the UML. These are, as we discussed, are the activity diagram, the use case diagram, the sequence diagram, the class diagram, and finally state machine diagram. As also we discussed in the previous lecture, when you develop a project, you will not use all of these diagrams. You will use it according to the project that you are doing. So embedded systems particularly are being used with the state machine diagram, which is our topic today and which is the topic I want to finish in this chapter. So let's have a look. The UML supports event-based modeling using state machine diagrams, which shows that system states and events that can cause transition from one another. They do not show the flow of data within the system, but include information about computations taken out in each step. It also shows the system response. The stimuli so are often used for modeling real time systems. What we understand from here is that while this diagram is particularly developed for embedded systems, it can be used for any event-based system as well. So if there is some kind of machinery that is a part of your system, or specific events are being executed so that the system state will change, you can basically use this diagram. It is possible to use it. The most frequent use that I see for the UML state diagram is that when some program is being embedded into the machinery, or while external entities are a big part of the overall system, such as you can, for example, show ATM machines or how a microwave works with using the state machine diagrams. Next, we can look into the structure of the state machine diagrams. State machine models show the state of the system, obviously, and there are certain states that you should be aware of, such as these are displayed as nodes and events, and arcs as nodes. When an event occurs, the system moves from one state to the other. So basically, you are drawing a state where there are three important situations: when you enter to the state, when you exit, and during the state itself. And this is called the state which perform an activity. State charts are an integral part of the UML and are used to represent the state of a system to indicate the activities. So whenever you start to a state machine diagram, what you do essentially is that you have a start, just as in the UML activity diagram. You have a start, initial state, and you have a finish, which is the final state. And in between, the system goes through one state to the other. Instead of focusing on the issues of the data flow and how this is flowing through the system, you focus on the state of the system and how it changes. Now, normally there are three important states for each three important activities within each step. These are the entry, which is the state of the system when it enters to that state. The exit, which is the state of the system when it exits from a specific state. And finally, do, which means what is the current state of the system. When you draw these diagrams, something like this will come out. We can zoom in to see it perhaps better. So this is just an example, as you can see. And within this example, we can say that the state machine diagram, as you can see, it has a start point where the execution starts, similar to a flowchart template. It can go into an internal state, and then the state itself will have an entry, exit, and do. And it can follow up other states as well. Okay, this is just drawn as an example, so it's not showing anything. But technically, when we show the states itself, unless some detail should be given about the entry, exit, and do conditions. There are some notations that you should be aware of when you use the state machine. So just like the activity diagram, you can see that there's a full circle and a full circle covered with another circle. This indicates the initial and the final states, which is the start and end. There are a couple of states. For example, the ones that you've seen up there are called internal states. These are called internal states, which shows the state of the system with entry, exit, and do actions. They are the integral part of the internal state. With entry, where you basically behavior that is executed whenever it enters to that state. Exit refers to activity or behavior that is executed when the state is exit, and do refers to executed while being in the state. There's also the state machine one, which is this one that you see in here, and this only has do. So basically, if you use it like that, it will only have the do activity and it will not have an exit or entry. So if a state is not changing when it enters or exits, you just use the regular state one. If it's going to affect it, either entry, exit, or both, then you use an internal state. That is the big difference between this one and that one. So moving on, we can look into the stuff that in here. These are done basically in Visio, because originally we were planning to do this in the class and draw them. But circumstances has changed. You can still find software like in Lucid Graph, similar structure, although not exactly the same. You might find similar structure about this as well. The regular state represents a static situation, such as an object waiting for some external event to occur, such as microwave or waiting or something like this. And the situation is that it has only the keyword to, something I already mentioned in the previous example. The internal one has entry, exit, and do. Again, this one I mentioned. The difference between internal and a regular state is that this one only has do. This one has entry, exit, and do all together. We have the note, which is used for, you can use it for a choice or basically for a comment. This is can also be used with other diagrams. If you make a restriction or attach remarks or notes, you can use a comment which carries no semantic force but may contain information about the model. And of course, you can use the gateway, which is basically the if else condition where it can go to a true or a false branch to evaluate it. There's also submachine state in the state machine diagram. Sometimes this is referred to as composite state as well, which is the next one. The submachine and the composite states are alternatives to each other. In other words, you can use a submachine state whenever you want to use composites. And the submachine state is the decomposition mechanism that allows factoring of common behaviors. So basically, if you want to group together related states, this is the state that you use, such as multiple states come together and forms a big state. In that case, you can use the submachine state. It is not something that I see very often, but in some examples, I see submachine states being used. So it is actually not wrong to use it, especially if you want to group your states. The problem with state-based modeling is that the number of possible states increase rapidly. So this is a big problem with the state machine diagram. Remember that these do not have to be an alternative approach. They have to be an abstract representation. And if you go over the top, this will actually create a system too complicated to drag down, and it might be difficult to design the state machine diagram. You need to create a balance, basically. Some of the details should be hidden. One way of doing it is to use the submachine state that encapsulates a number of separate steps. So basically, it allows you to divide a state that is too complex into substates so you can understand how this is going to work. That is the purpose of this submachine state. Do we have any questions? Anything you did not understand? No. As usual, nobody is asking questions. So I will give you basically a project which you're gonna, as I said, reverse engineer the project that you already completed and submitted yesterday. And in this project, in the second one, what you're gonna do is you're gonna decompose what you already built as if it's a system developed by others, and you're gonna generate the graphs. So we will assume that your project was completed with a plan-driven development this time, not agile, but plan-driven development. And we will also assume that you did not develop the project, someone else did. And what you're gonna do in here, you're gonna decompose the project and generate UML specifications as well as requirements for the project, so you can understand how this project can be decomposed or how else it could have been done if it was a plan-driven project. So you're going to learn both approaches. Okay, I said that is the purpose of your next assignment. And as I said, you will not have a midterm, you will not have assignments or quizzes. You will only have these projects for the 50 percentage of the course, and the rest, when the university decides what to do about the finals, we will then discuss it in a session. You know that I'm very open to communication. I will discuss it with you in one of these sessions about how to carry out the final exam. Okay? So let's look at this question together. it says in this question that we need to basically do an exercise about state machine diagram. It says that a microwave starts with displaying time during its power state. The microwave can be adjusted to work in different modes. This is the low state, the medium state, and the high state. And as you can see from this definition, it is possible from the very beginning that the microwave can change in between three different states. Having done so, having identified these states as low state, medium state, and higher state, each one will have a do operation, because when you set up the do for the low state, it will set it up to 300. When you set up the medium state, this is going to be 500. They are given in the question if you read it. And finally, for the high one, it will be 800. So low state, medium state, and high state, each of these affect radiation rate and runs the microwave. So because no exit or entry is given, these are going to be only states. They are not going to be internal states, because an exit or an entry condition is not given to us. So that is why they are going to be just states. Having set the power, the microwave enters to set timer. This is an internal state. See, it mentions in here that it is an internal state. So the regular ones, the ones that upstairs were just states, but this one, which is basically setting the timer, set timer state, which is mentioned in here, is going to be an internal state. The entry is set number 0, or no, it's just set number, sorry. Operation is countdown operation, which is going to be do. And exit state is when the timer ends, when the timer is 0. So this one, set number, is the entry. This one, countdown, is the do. And this one, the timer ends, is the exit. You can tell just how it is worded that it is an internal state, and it can basically, you can structure it to form. So 3 states coming into one state, and it will basically create the initial state. Having done so, a user can open the door of a microwave, which is an action that results disable state of the microwave. So if the user opens the door, it will go to a disable state, which is again a do state that stops the microwave. The microwave will pause at this point. Correspondingly, a user can leave the door closed, which will allow the microwave to be enabled and reach to the state where it heats the content. So in here, you have to basically do a decision. Is the door open or is the door closed? So basically, if the door is open, the microwave cannot run. So you will pause it. That is what it says in the question anyway. If the door is open, it will be paused. If the content is, if the door is closed, then it will heat the content. Both open and closed door of microwave are interactions. From here, you can understand that there has to be a selection, which means there is a gateway. Regardless of this situation, microwave can be stopped at any point, which then displays the time and stand on wait exactly like its initial state. So basically, you can connect the final state to the initial state. One big difference between state machine diagram and activity diagram is that the final states usually goes back to the initial state. Even if you don't show this deliberately, you know that the final state always connects with the initial state. Did you understand this example? Did you understand how you can draw this? Is it clear? So basically, when you want to draw a state machine diagram, those are the issues you have to pay attention. And I did this obviously before the class. I come to classes well prepared, as you know. So I draw this diagram to show you how this can work in a realistic scenario for the microwave. You see at the beginning, the microwave power was on, so it was displaying the time. This was given in the question. And you can set up a low state, which then set it up for 300, 500, 800, which was given in the question. If you go there, you will see it in the question that the power on state displaying the time. This is the start state of the microwave. Okay, look at the diagram that I have. So if I open the diagram, you will see that power on displays the time, and you can set up 500, 300, and 800. Once this is done, it goes to a set timer, which has entry, do, and exit. Look at the question. The question tells you everything. Each of these nodes affect radiation rate, runs at 300, 500, 800. Then you have set time state. This is an internal state. Okay, the difference between internal state and a regular state is that the regular state only has do. The internal state will have an entry, do, and exit. Okay, this is how you differentiate them. Because it's said in the question that this is internal state, it gives you basically the entry, what happens in the entry, which is setting the number. Operation is countdown, which is do, and exit when the timer ends. Entry set the number, operation countdown, do, exit state, timer ends. Look at what I did. Set number, countdown, timer ends. Then it comes to a decision. As I told you, you will come to a decision because this is an interaction done by you. When I say you, I mean the user. The user is interacting with the microwave, which then will affect its state. What you can do apart from setting the timer is to open the door of the microwave or perhaps close it. Doing so will affect how the microwave functions. When you open the door, obviously the microwave cannot run. So it will wait. It will go into a pause state and it will wait. When the door is closed and you set the timer already, which you did in the previous state, it will heat the content until it stops. So even if you don't mention this, actually the final state connects to the initial state, which means it will display the time, isn't it? That is how a microwave works. I'm sure all of you have used a microwave before, and when you look at this graph, it actually makes sense. This is an abstract representation of how a microwave functions. So we know from these diagrams that although it is specifically developed for software world, you can also use these diagrams, particularly the state machine diagram, to basically form a structured scenario to explain how this is going to function in an abstract scenario. Does it make sense now? Now that I show you the graph, does it make sense? Do you have any questions to ask?
Yes, sir. I have one question, please.
Go ahead.
When we are going to work on the next project, you said that initially when we started this chapter that most of these diagrams are not all used. It depends on the scenario or it depends on the project being worked on. So is it up to us to decide which of the diagrams we're going to draw, or are you going to include the information in the project
I will
details?
include the information for you. So you will have the option. I'm thinking about making the state machine diagram an optional thing for you if you want to draw it, because this diagram might not be suitable for every single scenario, particularly if you did a web page, for example. The state might not change, or it might not be very easy to show it. Okay.
Okay.
So I'm thinking about making state machine diagram an optional thing for those who want to go above and beyond. But all the other diagrams, you can actually draw them for any scenario, basically. This is a
Okay.
diagram specifically developed for machinery, for embedded systems, for anything that goes with system changing the state, because we are focusing here the state of the diagram, the state of the system and its interruptions. Okay, so you are not constantly interrupting a website, for example, but I can interrupt the microwave, isn't it? I can open the door, I can cut the power, and so forth. The user does not have always the power to do this in the system that you develop. So this is why I've been mentioning that there are different diagrams for different situations. I am well aware that this diagram does not fit into every situation, so I'm going to make it an optional. But for the others, I will give you a number. I will say that you, for example, you will have 3 sequence diagrams at least. But it's up to you to basically try to go above and beyond and aim for an A. I will just give you the minimum requirements and explain it. So do not worry. Whenever I give you an assignment, it is usually very detailed and it tells you exactly what you need to do. All right. Just be a bit more patient. I will announce it next week. Does that answer your question?
Yes, thanks.
Okay. Anyone else who wants to ask a question? No. Okay. That's perfect. So I'm going to go back and finish this chapter now. So as you realize, I'm not solving all of these questions. I want you to spend some time in here, although I have solutions for them. I do not solve every single one of them. I strongly suggest you to dedicate your time to solve every single exercise here, because it will help you to build up your understanding on the diagrams, how to draw them. You can also use any tools. I suggest Visio for those who have a Microsoft Office. And also I suggest Lucid Graph or online tools, as long as you can show me the diagrams itself. They have similar symbols, if not the same. So you can use online tools such as Lucid Graph, or you can use Visio to draw the diagrams. The slides here, as I mentioned several times, are prepared according to the Visio illustrations. So just to repeat what we covered in this chapter is that a system or a software model is an abstract view of a system that ignores some system details. It is not an alternative representation. It is an abstract view, which means many details could be hidden. Complementary system or software models can be developed to show system software context, interaction structure, and behavior. And we saw them how to do this with different graphs. We can use use case diagrams and sequence diagrams to describe interaction between the user and the system. We can use activity diagrams to show the flow of data, right? Having completed this, you can follow an object-oriented or model view controller architecture to separate how data is structured from how it is displayed, and hence why you can use a class diagram. Finally, there is the optional state machine diagram, which is basically going to show you internal or external events. State machine diagrams are particularly useful to display how hardware behaves and what state they enter. Okay, this diagram is particularly useful for hardware and software development together. Okay, when you consider them together. So whenever they come together to form a system, it is particularly useful for that, because the system obviously changes state that affect both. This is where I'm going to stop for today. It was a rather short lecture, but still it is we are coming to the 40 minutes limit. I have 9 minutes right now to finish the course. In the next chapter, I'm going to talk about system architecture, and we're going to spend some time on DFD, which is data flow diagrams. They used to be a part of UML notifications, but with the new version 2.5, they are not a part of it anymore. And as I said, a new UML version is being developed. And when it comes out, we'll probably need to update our knowledge about UML. So this is where I'm going to stop for today. Before I end my short lecture, do you have any questions? Anything you want to discuss? This is the perfect time, okay? So please express yourselves. No, you don't have any questions. All right, fair enough. I'm going to end up the lecture then, and I'm going to upload this recording to the YouTube channel into the class archive as always. Thank you for coming to my class once again. I really appreciate that you come every week, you listen to me. I cannot express how much I appreciate this. So I'll see you guys next week. Take care.